I'm Java Liu from the University of Illinois. I'm here to talk about our new work, coverage-guided tensor-compiler fuzzing with joint error plus mutation. This is a joint work done by researchers from UIUC, Tongji University, and Fudan University. Nowadays, deep learning models have been extensively deployed in various scenarios, such as auto-driving and code completion. A deep learning model can be logically represented as a graph of tensor operations being computed by the underlying deep learning frameworks. In the very beginning, deep learning frameworks are implemented as a library, where the model is computed by eagerly invoking their corresponding kernel functions. However, deep learning models can be computationally intensive, and implementing kernel functions from scratch requires significant engineering effort. As a result, deep learning frameworks have been actively applying compilation techniques to systematically generate high-performance code for various targets. Because deep learning compiler stack is more complicated and early developed, there can be many bugs in it, which limits its usability. To address this challenge, our goal is to automatically detect bugs in deep learning compilers. A typical workflow of tensor compilers includes three parts. First, the compiler translates a trained model into its graph-level IR and performs graph-level passes, such as simplifying algebraic expressions. Next, the graph IR is lowered into a low-level IR, for example, TIR in TVM. At this level, the IR looks like C, which allows the compiler to perform low-level optimizations, such as vectorization. Finally, the low-level IR is translated into the target code. Prior testing work such as Lemon and Cradle tests deep learning frameworks by mutating deep learning models at a graph level. In our work, we focus on another testing surface, which is the low-level IR. We build Tzer, a mutation-based fuzz testing technique, to practice the compiler passes with randomly generated low-level IRs. Let's first recap the general coverage-guided fuzzing pipeline. First, the fuzzer initializes a seed pool with a set of initial tests. For example, those initial tests can come from developer-written tests. By mutating selected test cases from the seed pool, we expect the mutants to bring us new coverage. If a mutant can reach new coverage, it will be considered as a valuable new test and thus added to the seed pool. The workflow of Tzer is consistent with the mentioned pipeline. Tzer regards the combination of an IR file and the pass sequence as the test unit. Each time it either mutates the IR or the passes and observes the coverage feedback from the instrumented compiler binary. Our test oracles include compiler failure and result inconsistency between optimized and non-optimized binaries. Once we find a test case with new coverage, we add it to the seed pool. We also do this in a loop so that once the pipeline is launched, it can be continuously running and generating new inputs to detect compiler bugs automatically. So, one key question in our work is how to generate new test cases, especially test cases that are likely to practice interesting compiler behaviors. In Tzer, we adopt a mutation-based approach where we mutate an old test case into a slightly different, but hopefully error-induced mutant. Specifically, we perform both general-purpose and domain-specific mutation for the input IR, and the corresponding pass sequences are also mutated to test the compatibility of various pass orders. We now introduce how to perform general-purpose IR mutations. In this step, we view an IR as an abstract syntax tree. The example here shows a function expression that consists of a simple while loop. To perform mutation, we first randomly select an AS node as a mutation target. We also collect its corresponding constraints, including type constraints and variable visibility. Those constraints are used in later mutation to preserve the compile time validity of the mutants, so that the mutants can often be successfully compiled. Next, we can perform three types of general IR mutations, including insertion, deletion, and replacement. For insertion, we insert a compatible IR ingredient to replace the original subsyntax tree. For example, we set the end node as a target node, and then we choose a compatible ingredient, which is a lattice expression from the seed pool, and use it to replace the subtree led by the previous end node. We can also do deletion. In deletion, we shrink the expression led by the target node by using a sub-expression. In this example, that is, we try to find a sub-expression under the subtree of the end node, which is the greater than node in our case, and then we substitute the original expression with the selected sub-expression. Lastly, we also directly perform single node replacement. In this step, we only replace the target node with any other node that has a compatible type. In this case, we only change the end node into another logical operator, such as the OR node. In addition to general IR mutation, we also mutate some specific IR patterns that tensor compilers could be interested in. Specifically, we target 3 IR patterns, including the loop hierarchy, memory access, and threadings. Those design choices come from the fact that low-level passes are mostly optimizing dense loop computation over a big chunk of memory. Tensor compilers focus on optimizing deeply nested loops. Therefore, we can insert some nested loops to wrap statements in the IR. Furthermore, different memory access patterns such as load and store can affect the data flow in the loop and thus have an impact on optimization strategies. Accordingly, Tzer creates new buffer access sub-expressions and insert them to the statements in the original IR, which change the data flow dependency. Lastly, the tensor compiler also models hardware threads and schedules them properly to maximize performance possibility. Accordingly, we can find a way to change the threading schedule of the program to observe interesting compiler behaviors. For example, we can assign different number of virtual threads binded to different loops, which can change the data access patterns of threads. So now we know how to mutate IRs and pass sequences individually. The next question is how to mutate them jointly to achieve higher coverage efficiency. If we just always mutate the pass sequences, the limitation is that many pass orders could have similar effects for the same IR, which is not coverage efficient. Another problem is that specific pass orders could always be producing the same bug, resulting in a lot of bug duplicates and a low compile rate. On the other hand, if we always mutate IRs, the problem is that only limited pass orders will be exercised. To address these challenges, our proposal is to leverage an interleaving factor called nmax to control the frequency between IR mutation and pass mutation. Notably, we prefer IR mutation over pass mutation because the third space of IR structures is often larger than that of the pass orders. Specifically, in addition to the IR pass pair, we use a value called n to record the tolerance of each test case. For each test case, we perform IR mutation for at most a max time, and if that cannot help find interesting new inputs, we switch to pass mutation. We consider interesting test cases as ones that bring new coverage and are compilable, so that all test cases in the seed pool can be valid. For evaluation, we first evaluate the effectiveness of bug finding. We implemented Tzer to find bugs for the widely used TVM compiler, and within a 7-month time window, Tzer has detected 49 bugs for TVM, where 37 of them has been confirmed and 25 of them has been fixed. We found that prior work are not able to generate some failure-inducing cases that Tzer is capable of. The best baseline, which is TVM fuzz, can only find 16% of bugs detected by Tzer. We also showed the effectiveness of pass mutation. We found that 54% of bugs will be missed if we don't apply path mutation. As a bug example, we found the basic block form conversion path in TVM violates the copy on write semantic of input IRs, which will make later passes fail. We found the root cause is that this path bypasses the copy on write class methods by using its pointer to perform in-place changes, which apparently violates the copy on write convention. As another example, the SSA conversion path did not carefully check if a vector element is empty or not, and this could result in out-of-bound read, causing the compiler to crash. We also evaluate the edge coverage of Tzer and other baselines. By running them for 4 hours, Tzer outperformed the second base fuzzer, which is TVM fuzz, by 1.75 times. We also conducted an ablation study showing that each subcomponent in Tzer contributes to the coverage growth. To sum up, we built Tzer, a coverage-guided tensor-compiler fuzzer that mutates IR and passes jointly. Our source code and evaluated artifact are publicly available on GitHub and Dorkhub. Thank you all for the attention.
And we've got a question from Jonathan Aldrich, and I will read it out loud. It's really great to see that a number of bugs were found and patched. Can you say more about the reception you got when working with developers to report and fix those bugs?
Okay, thanks for the question. We reported those bugs mostly on GitHub, and when reporting those bugs, we will basically like show a minimal reproducible, basically a very small test case to demonstrate this bug. There are cases, because we are basically reporting fuzzing bugs, there are cases that developer likes our bug, and there are cases that developers are confused, like how come like in real world such cases could be used. So we basically come from a opinion that we think it's always good to like improve the software or specifically the compiler quality by fix all kinds of bugs, including those ones that are less immediately useful. Yeah, I think I'm not sure if that answers the question.
So in practice, do you have a feeling how many were fixed by the developers, or do you have a feeling for that?
Well, I feel it's like 50-50. So it really depends on how urgent the bug is. So if it's mostly related to a critical path in the compiler, it usually gets fixed like much faster. And if it's like if it's a bug that are less likely to happen like in real world, like sometimes like it will be kind of ignored. Yeah.
Yeah, that's fair, but 50-50 is pretty good already. So that's great.